follow my notation. So X is gonna be maybe use Lipschitz. Okay, so I guess we can start now. So today we're gonna talk more on the constant C naught that we defined last time, and we're gonna prove that C naught is also like admissible in the sense that there exists a function U that is Lipschitz, so that U uh, is dominated from above by L plus C naught. Remember that we already proved last time that this is equivalent to the fact that U is Lipschitz, and we have h of x, the ux is less than equals to C naught almost everywhere. Okay, so that's going to be our goal. As always, um, do discuss with me, and do interrupt me if there are unclear points, or you know there are things that you would like to go deeper or further. As I said, we are already into the part that they are quite open-ended. I have raised various open, not just open problems, but also open directions that you can see. There are not a lot of tools out there to study deeply the problems. Okay, so let me recall the definition. So maybe this is a real line that contains all admissible C. So C is admissible if, so this is admissible if, uh, if, there exists U in Lipschitz, Tn, that you have h of x, the U x is less than or equal to C almost everywhere. So you collect all possible admissible C, right? And you would define C naught to be infimum of all of such, or such, right? And that's exactly leads us to the definition on the left panel. We define C naught to be infimum of all constant C, such that there's a function U that you have that inequality that happens almost everywhere. So in fact, based on this definition, you can write down equivalent form of C naught as follows. You can put C naught to be infimum over all possible function U in Lipschitz of the Tn, and you're taking essential supremum over x in Tn of h of x dux. Okay, so the first part is that you're taking essential supremum, right? Because U is Lipschitz, so this is defined almost everywhere. You can take essential supremum, and it could be, it couldn't be, it couldn't be infinity, because du is bounded almost everywhere, right? So it's essential supremum is finite, and you're taking infimum over all of those, and this gives us a quite beautiful formula. So this is, you see that this is the first formula that you can see. This is the second formula that I'm writing it down here. So now we're going to prove a simple result, and I mean, I mentioned it last time, but today is a bit more precise. So we're going to prove this first lemma that C naught is finite, so it's quite well defined. It's not vague, meaning that it's not minus infinity, and we have a nice bound uh, that this is the case. Okay. Um, so I mean, in the terms here that we have the C naught is well defined, finite, and again, let me rewrite it here because I'm gonna just use it. So you take minimum over all x and p. This is going to be less than or equal to C naught, less than or equals to maximum of x in just the torus of h of x0. Okay, So I mean, I'm highlighting the left term here on the chain of inequality. The reason why I can take minimum over all x and p is because h is superlinear. So when p gets really large, then it's going to infinity. That means that minimum exists. Okay, and again, x is in a torus, which is compact, so I'm not worried about that. Um, so how do we prove this result? I mean, you can look at the formula 2 over there, right? 1 or 2 doesn't matter. So I mean, the first step is that you chose, or we chose, you know, any possible functions that we can test, right? So I mean, just take one test function, phi equal to 0, to be a test function, whatever that means, right? Because I'm using formula 2 here, for example. I can take essential supremum over all possible Lipschitz functions, right? The Hamiltonian acting on that, so I can just take phi to be constant or 0 functions, and we see that h of oops. So we see that h of x d phi x is nothing but h of x0, and clearly this is less than or equals to max of h of x0 for all x. So that's simple, right? And so you get the first conclusions that C naught is less than or equals to max of h of x0, right? Because your C naught is the infimum over all possible functions, possible Lipschitz functions, right? And phi identically equal to 0 is just one such choice, right? So we make a choice, and then we see that already. So on the other hand, we see that, clearly that for any, second point is that for any such choice of, Lipschitz functions, clearly that, again, it's defined almost everywhere, right? Um, so you would have that the Hamiltonian is defined almost everywhere. At the points that is defined, it's always greater than or equals to the minimum value, and clearly that this has to be less than or equals to C. I mean, C here can also be rewritten as, maybe let me write here. So you would have that mean of, oops, mean over all possible xp of h of xp. This is less than or equals to h of x du x, less than or equal to C. C here is just the essential supremum over all x in the torus of h of x du x. Okay, so you have that this one is always less than or equals to this one for all possible choice of u, right? So you're taking now, you now take inf over all such u, then you would get the result. I'm highlighting on the left panel here that C naught is greater than or equals to the mean value of h, right? So we are done. Okay. So this is a simple bound. It turns out to be quite a useful bound that we can use. We can use for our analysis later. I'll tell you when it comes. Okay. Now, I didn't include the formula here, but now I want to give you the third formula for C naught. And then I also want to give you an example before we moved on to the point that we're gonna prove that C naught is also admissible. Okay, right. So how should I do it? Actually, I want to leave this space for later. So let me actually go down. Okay, so that I'm not using that space. So now let's do the third formula for U naught, C naught. And then I'm gonna just copy the formula above, to the above. So the second formula reads that we have C naught equals to infimum over all possible Lipschitz function And here I'm taking essential supremum of x in the torus of h of x dux. Okay. Um, so again, the key thing is that u is only Lipschitz, and then I'm taking essential supremum here because it's not defined everywhere. So now I give the third formula, so third one, that I'm gonna replace Lipschitz functions by C1 functions, and I can still make the same conclusion. And actually we have done the proof, it's just hidden in everything we have done. So this is the third one. C naught is gonna be infimum. Instead of taking Lipschitz function, I'm taking u to be C1 in the torus. And, or actually it could be C infinity, so C1 is just, And because when I'm taking C1 functions, I don't have to take essential supremum anymore. I can take the max. So max of x in the torus of h of x du x. Okay, so this is our new formula. So people call this one this is the so-called Imp Max Formula. Okay, so this is also written in my book. You can double check that. It's quite fun. Okay, so let's see, how do we prove this? Well, what's the best way? Okay, so now let's compare the two right hand side. The two right hand sides here, right? The below one is that I'm only taking infimum over all C1 functions, right? So clearly that, so as we see that C1 functions is just a subset of Lipschitz function, then clearly that, if I'm taking infimum over more functions, I should have something possibly smaller, right? This one should be possibly smaller than just taking infimum over a smaller set, right? Okay, so that's that. So we already got one-sided inequality, right? So now, next, we prove the converse, right? That, although I'm taking infimum over a big set of functions, I'm still fine. I'm not, overdoing it. And I claim that we have done this. Why? Because if you recall that we take u in the set of Lipschitz functions, we know already that h of x du x is going to be less than or equal to c, and c, this one is nothing. You just define it to be essential supremum of x of h of x du x. Okay, so as usual, you have only used Lipschitz, so it's not defined everywhere, and our one of our tools is that we can smooth it up, right? You just define u epsilon to be eta epsilon convoluted with u, like in the previous lecture, right? If you define so, then you can see that exactly based upon our calculations, we have h of x du epsilon x is going to be less than or equals to nothing but c plus c times epsilon. So you pay an additional price, but you are there, right? So h of x of du epsilon is just less than or equal to c plus c epsilon. And if you let epsilon goes to 0, you're fine, right? So that means that we are done. Okay. So yeah, so let epsilon goes to 0, we get the converse inequality, and we are done. Okay, so that's rather remarkable. You see that the tool that we developed earlier, that was quite simple, but it's really useful, right? That smoothing up technique. There are other ways to smooth up functions in this theory as well, but so far, because of convexity, we often use this one. So let me pause here. Any questions or concerns or things you want to discuss here at this moment? Anything you want to talk about? Okay, so seemingly that's simple enough and quite clear. So by the way, this Imp Max formula is not something uh, too easy. This was only done by dynamical system people and PD people in around 2000s. So it looks simple, but rather beautiful. So let me make a remark. So in PDE, people often call C naught also an additive, also the additive eigenvalue, okay, of the PDE, and the Imp Max formula is an analog of the Imp whatever Imp formula for the principal eigenvalue of elliptic PDE. Okay. So the principal eigenvalue for the elliptic equations often, would read that if you have the equation LU equals to lambda U, then it would, the principal eigenvalue lambda 0 would often can be written down as infimum over all phi, that is in H01 of U or something like that, and you're taking the integral of over U of LU with U. No, this is not the correct way to write it. It's in the weak form. Okay, let me write this one. LUU over the L2 norm of U. L phi of phi over phi in L2. Okay, so that's a reminiscent, or an analog of this formula. And later on, if I have time, I'm gonna give you one example of how do we go from additive eigenvalues of this kind of problems to additive to principal eigenvalue of the Laplace operator in one example, but that's for later. Okay, I don't want to go too far at this moment because that would be a little bit distracting. So I want to give you an example about how to find C naught, right? In one clear example, and you can see it from there. Okay, so let's consider exactly the classical mechanics Hamiltonian. And I want just to make sure that we are not going too far with with this classical mechanics Hamiltonian, we want to stick with that and make sure that everything is clear. Okay, so it could be plus v of x or minus. I'm just putting minus here because I just want to make it easier. So I'm looking at this Hamiltonian h of xp equals to 1/2 p square minus v of x, and I'm considering for x and p that are in the torus cross Rn. Okay, and here v satisfy that minimum of v on the torus equals 0. Okay, so I mean geometrically the graph of v is going to be, I'm just going to be drawing a picture in 1D, then v can be like that. So it's goes up like that, it's periodic, so the value has to agree at the 2 points. So v has minimum value at 0 at certain points here in this picture, so maybe 3 points. Okay, so this is the example of mean v equals to 0 in the torus. Okay, so the question now is that what is the constant C naught, right? I mean, what's its value, and can we compute it? And so my general answer is that that in principle it's quite hard to compute the value of C naught, but in certain cases we can do it. And also that there's a method so-called asymptotic expansion at infinity, that if we go to infinity, then we can find the asymptotic behavior of this constant. So that method is also written in the book. That's quite new, but that's also for later. For now, we are just at 0. We want to compute what is C0. So let's do it. I mean, I want to naively see what's going on with this thing, right? So naive ways, a naive way to think about this, right? So I'm just gonna write out one formula, right? Again, I mean, you can actually do it in many different ways. I'm just using exactly the formula we just wrote down, right? So the imp sub formula. So imp phi in C1 of the torus and max of x in Tn of h of x d phi x. Okay, because we have an explicit form of the Hamiltonian, so this can be written as imp of phi in C1 and max of x in the torus, and I can just write out explicitly what is h, right? So it's going to be max of 1/2 d phi x square minus v of x. Okay. Right, so let's see, what do we have? Well, on the one hand, you can just do a very crude analysis, right? You can say that this term that I'm highlighting here is always, this one is always non-negative, right? So, on the one hand, I can just throw it away and see what's happening, right? So if I throw it away, then I have that this is going to be less than or equals to, because I'm throwing it away, infimum of all phi in C1 and max of x in the torus of minus v of x, right? So that's what I have. And you see that now this infimum doesn't play any role, right? Because I have actually finished handling with phi. I have sort of just thrown away that term involving phi, so the inf over phi is is negligible, right? So that's gone. And I know that v v is non-negative, or mean of v is 0, right? So max of minus v is gonna be exactly 0, right? Because I'm flipping V back, so max is 0, so this is 0. So we get right away that C naught is less than or equal to 0. Okay, so that's exactly the first thing that we can see. Okay, now how do we get the other way of estimating C naught? Okay, so the other ways, hold on, I think I wrote that something wrong. Give me 1 second. It should be greater equals, I'm sorry, this is totally wrong. That's why I was quite confused. Yes, I'm throwing away something non-negative. It's greater than equals to, so C naught is greater than equals to 0. Okay, sorry about that. Okay, so that was good. Now, so next, for any phi that is in C1 of the torus, I'm trying to see what is happening, right? So how should I deal with it? I mean, should I take any phi in C1, or should I just pick up a, an obvious phi, right? Because remember that we are taking infimum of all phi, right? So that exactly comes into play the earlier bound that we have. But I mean, in case that we are, we want to repeat it, I'm not gonna take any phi in C1, right? I just choose C. I mean, I'm just gonna delete this one. I'm not taking any, right? Because I can choose it. So choose it just to be exactly the constant function 0, right? Then we would have the C naught should be less than equals to exactly max of x in the torus of 1/2 dc x squared minus v of x. Okay, and you see that exactly here that this is 0, so max of minus v is again 0. Okay, so I have been able to conclude that C naught is less than equal to 0. Okay, so from those two we get that we get that C naught has to be 0. Okay, so that's the conclusion. Is it clear? Any question for me at this point? I might have sort of messed up with some inequalities, so do correct me if I'm writing down some inequality wrong. Okay. Yeah, I guess that this one is okay. Okay. So again, I mean, so let me write down this one right away with you in this example, and then we go back to the final result for today that I want to present. So recall last time that we defined the effective Hamiltonian H Hamiltonian H bar, that we define H bar P. So instead of just defining at the point 0, I'm defining for every point P. And by the third equivalent definition that we have been able to prove today, H bar P can be defined to be inf over phi in C1 of Tn max of x in the torus, H of x, P plus d phi of x. Okay, so we have this formula, and we know that H bar is convex. Okay, and in the above example, then clearly H bar of 0 is just C of 0 equals to 0, right? So that's quite nice. But as I said, in general, the open problem is, to understand deeply the behavior of H bar. Okay, I claim that even that in the early example that we can have H bar of 0 equals to C of 0 equals to 0 in this very specific example that I'm putting a box around here with V having mean equal to 0. In that example, in general, it's really hard and impossible to write down the explicit formula for H bar. In 1D, then you have certain implicit formula, but in general, you don't have it. And you have H bar is convex, so it's differentiable almost everywhere, and also twice differentiable almost everywhere. But its sets of singularity can be a counter set or can be something very complicated. So the question is to understand deeply the behavior of H bar, and in particular to so to understand where does H bar behave nicely, and what is the set of singularities of H bar. And all of those are really important, and up to this moment, even in 2D, there's not a lot of understanding of H bar. I mean, we have better understanding in 2D. In 3D and higher is really complicated, and this is extremely important problem because it connects to a lot of fields. I mean, from PD dynamical system, and also this functions is actually related to first passes speculation in probability theory as well. So I mean, it's something extremely hard to be understood. Okay, so that's the thing I wanted to discuss more. Now let's get back here. So I'm gonna write out the third formula, and we can get away with that. So C naught equals to Imp phi in C1 Tn max of x in Tn of h of x d phi x. And for H bar, we do have the formula that H bar P equals to Imp, let's change it to C, and max of x in the torus, H of x, P plus dc of x. Okay, so those are the formula we have, and you can use them from now on. They are quite important, fundamental, and they give us certain good information, but to go really deep, this is not enough. This is just giving you very, in a way, generic and qualitative properties. Okay, right. So now I'm going to prove that, so recall that, in the above here, I have written it down. You take all admissible C and you are taking the infimum, right? It's not clear at all if infimum itself is also admissible in the way that there is a function U that satisfies that h of x du is less than equal to C naught. So we now prove that it's also admissible. And this is actually not easy. I'll tell you. Okay, I take it back. Um, uh, it's easy if we look into that in a correct angle. I have thought about this when I was writing this one down, and 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 if we look into that in a wrong angle, it's not too easy. Okay, so let's prove it. Um, and then I'll mention to you why. Okay, so we claim that there exists a Lipschitz function so that U is bounded dominated by L plus C naught, or in other words, this is equivalent to this. Okay. So now prove, stability result, right? I mean, you have C naught and you say that, so graphically, this is C naught. And because it's the infimum, right? So we can choose a sequence C1, C2, CK admissible sequence that converging to C naught, right? So CK admissible, CK converging to C naught, and CK admissible, meaning that you can find UK that is being dominated by L plus CK. Okay. So UK dominated by L plus CK. And now I'm going to normalize it. Normalizing it meaning that I'm subtracting the value of UK at 0. Okay, so I mean I have UK is dominated by L plus CK, and this is equivalent to the fact that h of x the UK is less than or equal to CK, right? Almost everywhere. Okay, and the problem is that from here you see that from this bound we automatically imply that not equivalent. Imply that the UK in L infinity of the torus is bounded by a constant independent of K, because our Hamiltonian is superlinear. However, it's not enough to conclude that UK itself is bounded, right? Because UK actually, you can shift it, to any constant. It still starts satisfying the same thing. That's what we proved earlier. So we have to normalize it. So what we are doing is that we are sort of subtracting a constant, subtracting UK at 0. Okay, and ask you to check why that you have this thing, right? Well, I mean, I just claim already that you have DUK tilde is bounded. How do we see UK is bounded? Well, you look at the torus, that your torus is exactly a, 0, 1 to the, you can identify your torus to be this cube, right? 0, 1 to the power n. This is 0. Any point axiate of the distance at most root of n to the point 0. I mean, in fact, you can make it better because this point and this point, are identical. So, so you can make it better. But I'm just saying that you can see that UK tilde of x is going to be equals to UKX minus UK of 0. And this is surely less than or equal to root of n times the du k in L infinity, less than C. Okay, we are just using the Lipschitz property. Anyhow, this gives us that UK tilde is also bounded. So because UK is bounded and is UK tilde and is equi-Lipschitz, so by Azela-Ascoli, you can find a subsequence UKJ that converges to U uniformly. And the Lipschitz property is being inherited right away. Okay, so we have already that CK converging to C naught. UK tilde is also dominated by L plus CK, and UK tilde converge to U uniformly, right? So it's a stability result. So we now finish the proof by showing that U is dominated by L plus C naught, or equivalently h of x dux is less than or equal to C naught. Okay. So this comes a point that we have two options, right? You see that we have two options to go. We can either deal with the Lagrangian framework, or we can either look into the PDE, right? So I chose the Lagrangian framework. Why? The Lagrangian framework here is easier. It's easier because of the fact that I have already UK converging to U nicely, and that's exactly the point. I think that I'm abusing of notions here. I'm writing UK to be UKJ. So you see the Lagrangian framework here saying that for any curve gamma, we have, you know, UK gamma B minus UK gamma A is bounded by the action functional normalized acting on gamma. And because UK tilde is just UK subtracting a constant, so that holds also for UK tilde, right? Exactly the ones that I'm highlighting on the left panel. Let me put a box around it here. Okay. And we have uniform conversion, you know, UK converging uniformly to U and CK converging to C naught. So you just pass the limit and get the result, right? So we have that exactly U is dominated by L plus C naught, right? We are done. Okay. So a remark here, we used the Lagrangian framework as its clear and stable under uniform conversion. Okay. So the last point I want to highlight is that the PD framework is actually harder. Well, I wouldn't say harder, so I put it in quote as, okay. What do we have? We have h of x duk tilde is fine. It's less than equal to ck almost everywhere, right? And we have uk tilde converging to u uniformly, right? That's also okay. Now, again, I mean, this is, you know, some of you here experts in viscosity solution, then you can say this is obvious, but assuming that you don't know viscosity solution, whatever that means, you know, I'm asking you to prove a stability result, right? I have h of x duk tilde is less than equal to ck only in almost everywhere sense. I have uk tilde converging to u. I have no ideas about its gradient, right? I mean, whether it's gradient converging to duk tilde converging to du or something. I mean, surely in a weak sense, but I mean, not in a strong sense. So here I ask you prove that h of x dux is less than equal to c naught almost everywhere, right? I would say that this is not easy. It's a stability result. It's not, it's just not easy. You know, you can check me, you can try to prove it directly. Um, if you know stability results in viscosity solution, and this is exactly that. But assuming that we don't have that, we are just proving some conversion in result in analysis, and this is not clear because I'm not sure what's the conversion of du tilde to du, right? In what sense? It's not in the pointwise sense. So how do I conclude that? So, but you see that if we write the proof like in the lab panel, when we are using exactly the Lagrangian framework, it's just so easy because we have stability of everything of under uniform conversion. So already here you have seen that after 17 lectures of developing everything, you know, step by step, everything is simple. But now you already see that sometimes using one viewpoint is much harder than using the other, you know. So that's that. So I mean, you know, that's a very important remark, saying that it's just not easy. Later on, when we see PD framework, we're going to see that this fits into the so-called theory of viscosity solution for Hamilton-Jacobi equations, and it's a stability result. It's quite standard there, but you know, standard under the fact that we have developed the whole theory for that. Okay. Uh, so there's another proposition on the lab panel here that I'm skipping. it's just standard from the definition saying that if gamma is calibrated on a set of nested intervals, then it's going to be calibrated on the union of that, which is the biggest interval, and also that calibrated curve is stable under C1 conversion, which is obvious because if you write out the action functional, so the first claim here is this one is obvious from the definition, and this one is also obvious in the sense that if I have the integral from a to b L of gamma k s gamma k dot of s ds, because I know that gamma k converging to gamma bar in C1. Again, this conversion is in C1, so as k goes to infinity, this is just converging to L gamma dot ds. So clear gamma bar, sorry. So clearly the gamma bar is calibrated as well. Okay. So we are done. Okay. So I guess that we have time for questions or discussions. Anything that you want to comment? Or if you see a quick proof of this claim in the PD language, let me know. Actually, I was also thinking about this, and I couldn't find an obvious proof, direct proof.
Can you talk about the analytic eigenvalue and the example connection with Laplacian?
Okay. Okay. Yeah. So okay. So let me put it this way. So in general, additive eigenvalues occur in all kinds of nonlinear elliptic PDE that have maximum principal. So for example, you can search, there are lots of paper on additive eigenvalue or principal eigenvalue for nonlinear elliptic PDE. And there are lots of paper occurring regularly on the archive and also in publications. So one particular example that people often talk about is the example when I consider the equation like, okay, let me try to write in a correct way. So minus Laplacian of u, so I'm putting the Laplacian here, plus du square equals to c naught in the torus. Okay. So hold on, no, let me also making it also, I could put 1/2, but that's fine. I'm just gonna put c naught in the torus. Okay. So again, v here is given in ctn or something like that, or if you need more smoothness, you can assume so. So I'm looking at this equation, and as I said, C0 is the additive eigenvalue of this problem. This is not a first order equation; it's a second order equations. But this example comes also from in terms of Vardan works, it comes from the rate functions in large deviation theory as well. But a way that we can see this problem that is it has a relation to principal eigenvalue to Laplace to the Laplace PD. It's just a simple Hopko transform. I think that this thing was so I let phi equals to e to the minus u. I guess I might be wrong in terms of the size. If I'm wrong, I'm gonna go back and check it. So let phi is e to the minus u, and you just compute. So you have phi xi equals to either the minus u times u minus u xi, okay? Phi xi equals to either the minus u. You can differentiate this one twice, so you have u minus u xi, or if you hit the derivative on the exponential, you have uxi squared. Okay, so this helps you to compute the Laplacian of phi equals to either the minus u times minus Laplacian of u plus du square. Okay, I think I got the correct sign. So now you multiply your PD with phi, which is this is phi, right? So you would have that Laplacian of phi plus Vx multiplied with phi equals to C0 multiplied with phi. If I'm not mistaken, I think so. So again, if you put the minus signs to make it to be an elliptic operator, you have minus phi, Laplacian of phi minus v of x phi equals to minus c naught times phi. And clearly, minus c naught here is the principal eigenvalue of the operator minus Laplacian minus v. Okay, so that's a link, and up to date, the question of understanding this principal eigenvalue or understanding this kind of problem, you know. So another open question is to understand the problem of minus Laplacian of phi u epsilon. I put epsilon, so it's a vanishing viscosity plus du epsilon x square equals to c epsilon of 0. So question, what is the asymptotic behavior of u epsilon as epsilon goes to 0? And what is the fine details of the expansion of c naught epsilon 0 minus c0? So this is still an open, quite a big open problem in the field, and this has linked to spectral theory, of course, and you know, there are lots of people in working in PD or mathematical physics interested in this problem. For example, Barry Simon has written a lot about this problem, and they talk about sort of like what happens if you perturb V a little bit, or what happens if you try to, you know, understanding, you know, the details behavior of C epsilon minus C naught. And there are some problems in the literature, they call it, you know, flea of an elephant, saying that, you know, you can think of V as an elephant, the potential energy, and if you perturb it a little bit, you put a flea on that elephant, then what happens? And so far it's just quite open, you know. So yeah, just that. And this kind of transformation, this is a Hopko transformation, and it's one of the key points to go from large deviation to Hamilton-Jacobi-Bellman equation as well.
Thank you.
Okay, good. Yeah, I'm afraid that I'm telling you too many open problems. Maybe it's not good, but anyway, whatever. I mean, this is, for example, this is one of the problems that I have been also wondering around a lot. For question is proof that as epsilon goes to 0, u epsilon, whatever. For example, u epsilon, you have to normalize it by a constant, doesn't matter. Does it converge in a full sequence at epsilon goes to 0 to a unique function u, solving the equation? No, I am missing v here. I mean, I'm writing nonsense. I'm sorry. Let me modify. Do you have that this one converge in the full sequence to you uniquely, you know, so that you solving the limiting equation, which is a first order equation. So I myself try a lot and failed a lot. So that's what I can say. Okay. Yeah. So actually, in my book, I also listed this one as one of the very important problem. I know that many people have tried and failed, including me. So anyway. Okay. Yeah. So if there's no other question, then thank you all, and then I'll see you on Friday. Right. So let me stop for now. See you later.